Hello everybody. Today we have very thin participation in the class. Hopefully everybody is healthy. I heard that a few students actually got COVID, so hopefully it's not a big deal. So today we want to finish what we discussed last lecture and also add the privacy aspects of things. So hopefully we can wrap up the discussion on machine learning, security, and privacy today. And this would be basically the checkpoint for your second quiz. So last time we discussed ways to attack the machine learning system either during the training phase and also during the inference phase. And we basically said that the main thing that happened is an adversary creates this what's called an adversarial sample, right? And by querying the system or creating some sort of a shadow model, the attacker can attack the system. And the goal of the attacker is fooling the system in order to make the incorrect decision. And that incorrect decision could be either targeted or it could be untargeted. So basically anything but the correct label, or in some more sophisticated scenario, could be exactly what the attacker wants. So now today before jumping into the new topic and concepts, we want to also discuss what we can do in order to prevent this type of attacks, okay? So for the poisoning attacks, for attacks during the training, there are various ways of making the system more secure. I'm not going to go through the exact details. Hello. But just to give you an overview of what's going on and what are the potential offenses. So if you remember when we talked about poisoning, we said that essentially we're going to have a space with multiple different inputs, and then basically we're gonna create this decision boundaries, something like this, that we said, okay, if this within this boundary, this would be class 1, this would be class 2, this would be class 3, and so on and so forth, right? And if you remember, we said that essentially what the attacker does is creating this adversarial samples that are very close to this decision boundaries, but they actually, for example, belong to this class, but they actually are on the other side. And what will happen is that this will shift the decision boundary and basically mess up with the way that the classification should work. And during the attack time, basically the attacker used this area to create their adversarial sample, right? So a natural defense against this is basically making sure that your decision boundaries can tolerate a little bit of noise. So in other words, if I want to redraw this image, what I mean by that is when I'm designing this way, there should be some sort of a guard band for each of these boundaries, so that if this boundary shifted to this way or this way a little bit, still I can correctly classify my my label. So if all of these labels are not within this slight guard that we are adding, all the labels and all the data are in this other side, then adding a slightly perturbed input doesn't shift the decision boundary, but doesn't have any meaningful impact on the classification problem. Okay. So basically, when you're doing the training, you can create a more robust training set, such that it actually can tolerate a little bit of changes into the inputs. And this way, you basically kind of like acting proactively as an attacker as well when you're training your normal system. And think that if the attacker is trying to add this little bit of, remember we said that basically what the attacker does is takes the inputs and add this very small noise and then keep adding this until it can actually manage to flip the label. If we actually can tolerate a little bit of noise and still get the correct Y, then we are kind of immune against this type of noises. Of course, at some point, the noise could be so large that the attacker can flip this, but that would be big enough that we can probably detect it with other things. Okay, so it's kind of like, we're making sure that our system in some ways is noise tolerant. Okay, and two things that we can do. One is during the training, we can do it. If you remember when we were talking about gradients and the way that we do the training, be careful. We can also, when we are actually doing the gradient descent, we can add these perturbations and making sure that the system is robust against. Okay, so these are usually this is called adversarial training. Basically, the adversarial training is this idea of we are proactively adding noise ourselves to our system during training, and this way we hopefully can kind of like mitigate the effect of the attack. Does that make sense? So it's kind of like, this is like basically this group of defenses is talking about adversarial training. Another group of things that you can do is basically just making sure that your model or your data set is protected. Remember when we talked about poisoning data, we said that we have a set of normal X and Y's. And what the attacker needs to do is it's kind of augmenting this with their poison samples, right? With X and Y primes, X2 and Y prime 2, and so on and so forth, right? The attacker needs to either change these labels to incorrect labels or just add additional records to your data set, right? So if you actually have a full control over your data set and making sure that data set that you're using for training your system is coming from somewhere that is secure, or at least there is some guarantee that the system has not been modified, then the chances that the attacker can actually poison this data set is pretty low. Okay, so it's kind of like you're only trusting sanitized data or collecting data from of trusted entities and trusted parties. Okay, and this way you definitely reducing your attack surface, which means that you're reducing the chances that this data set that you're working with is actually indeed poison. Okay, and you can do the same thing with your model during evasion attack. Remember, for the model, we said that the attacker basically needs to query this model to train their adversarial sample, right? So kind of like back and forth, create a new adversarial sample, query the model, train their system in order to actually find eventually that adversarial sample. If you can actually somehow control this part and doesn't allow the attacker to infinitely query our model, or at least having some sort of detection mechanism if it thinks something is malicious, then the chances that we can actually detect these attacks and protect our attack is pretty high. Okay, so in general, protecting the model or your data set is one of the ways that you can kind of eliminate this attack. And when we are saying protecting the model and data set, basically in this case, your model becomes a regular software, right? So the way that you protect your rest of your software, the rest of your operating system, you basically protecting your systems. Okay. The fourth thing that you can do is finding the applicant.
So I was kind of confused. Could you repeat kind of how we protect the model and data set?
So for protecting the model, what you need to do is basically, so you need to think about what the attacker needs to do, right? For poisoning attack, the attacker needs to change your data set in some way, right? So when you're collecting your data set, making sure that this data set has been collected in a secure manner, then the chances that there is an adversary during that process is much lower, right? So you either so typically if you think about just pipelines for machine learning, is the way that it works is that you either collect your data set yourself or you buy it from maybe some other entities, and then or collecting it from some different users, and then train your model. So if you only collect it from trusted user or making sure that they actually collect it in a secure manner, then the chances that the attacker can change those things and modify those things is much lower, right? Uh, so it's kind of like think about it as a secure lab or secure, building, right? So if you actually have guards and have locks and have doors, then the chances that the attacker can actually go in there and change something is much lower. So the same idea for both the model and for your data. All right, so the fourth thing is finding the outliers. And this is specifically very interesting because if you think about this, again, these two things that I'm showing here, if you remember at the end of the day, when you're want to, for example, poison the data set, what we are doing is we are kind of like, having the same input but with different label, okay? And if you actually look at the distribution of all these, different records here, you will see that actually the one that has the same features but different label, so it's supposed to be here, but now because we are kind of like changing the label, it's somewhere here, right? Or the other way around. And if you look at the distribution of this, you will see that this is basically doesn't fit into the same distribution that all these other records. So in some sense, basically, when you're intentionally change the label or the features of one input, you engineer those features as an adversary, what you're changing in reality is changing the distribution of that record. So the record no longer fits into the same distribution, or at least act as an outlier to that distribution. And if you have some sort of outlier detection mechanism, which is very common in statistics, the chances that you can actually find these outliers and remove them from your data set is pretty high. So what you would do typically is that you, before training actually, what you will do is doing some pre-processing. And during this pre-processing process, you just find these outliers and remove them from your data set. And this way, you again decrease significantly the chances that the system is poisoned. So even if it's actually someone tries and adds some poison samples, since you're doing the pre-processing, you can find some of those outliers and remove them. And finally, you can just, either manually or automatically inspect your system. This is again just going through your records and labels and see whether there is something that looks obviously wrong. Again, given that what will happen is these adversarial samples have different features with completely different labels, you might be actually able to detect this. And remember, for example, we said what we talked about. Things like backdoor attacks, that we said that, for example, the attacker can add these known samples to the record, and this way they can always train the system to make a wrong decision. So if you manually inspect your data set, you probably can see there are examples like this in your convenient data sets, and you should be able to detect that. Yeah.
We read a paper earlier in the quarter where it was talking about how any machine learning model can be reverse engineered if it's deterministic. How do these protections relate to that?
This actually, when we're going to talk about it in this lecture. That's a privacy problem, right? So if you can reverse engineer your model, then that becomes a privacy problem. We actually have to talk about it. We call it model extraction attacks. And yeah, we got to talk. Okay, so the fifth thing is basically inspecting your data sets with various ways. And the hope is finding things that are obvious, right? And then hopefully you can find. So this is kind of like, the defenses for specifically for poisoning. For evasion, you also kind of like, doing almost similar things. So the adversarial training is one of the things that you will do. Gradient regularization is also kind of like adding some sort of perturbation to your gradient. So again, these two things are going back to this idea of, given that the adversary is trying to add some noise to your model, and then using that noise trying to flip your label, What we can do is that during the training, we should be aware of this and we should train our system to be robust against these small changes. All right. So that's the basic idea of the test. Detection is another way of protecting your system. I already discussed this, that for example, if you see that somebody is keep sending queries to your system and requesting some data from your system, you can basically train some sort of anomaly detection on this system and then see that whether this behavior is a normal behavior or not, right? So if somebody is keep requesting something and probably this is not something that you normally would see, chances that this user is potentially trying to create some sort of adversarial sample is pretty high. So you can have some sort of a detection mechanism for your system so that you can see that there is an intruder, there is some sort of anomaly attacks in the system. Okay. And finally, there are pure machine learning methods in order to protect your system against these attacks. I won't, actually go through the details, but generally the idea is if you can actually run some tests or do some validations of formal methods in order to see that whether the system is actually indeed, for example, robust against certain type of attack. So think about it as some sort of list of tests that you run and see whether this trained model is indeed robust against this type of attacks. Any questions about the defenses, poisoning or evasion? So to just summarize, we usually do three things, right? One is making sure that the training is robust against noises. So that's number one. Number two is that we do some sort of protection for our system, making sure that the data set or the model is protected. And then number three is some sort of, data analysis or machine model analysis methods, such as finding the outliers, compress the network, so to reduce the overfitting and so on and so forth. So we do either some statistical, tests and methods. We use some sort of, just general security principles, such as making sure that the system is not modified. And then the big thing is basically using this adversarial training. So to make sure that our system can tolerate a little bit of noise when it's actually trained. Okay. So to just finish this part, there you might also think about, okay, what would happen even before training or after the inference, right? So there are actually since the machine learning itself is, as I said, it's basically a system. Before the deployment or after the deployments, there are groups of attacks that can happen, right? So for example, one thing that can happen is during the data collections, right? So this is well before you actually start training your model. You're just collecting data, because any machine learning system starts with a large data set and a data collection, right? So an attacker can basically, what the attacker can do is trying to mess with this data collection form. That could be by creating fake data in your system. That could be by adding bias to your system. That could be by spoofing your sensors, whatever that sensor is. And in all these cases, what we want to do is we want to create faulty data, right? And eventually add some error and add some unexpected behavior for the system. Okay. And again, this is nothing to do with what would happen during poisoning and what would happen during evasion. It basically can happen well before your system is being trained. The second thing that can happen is that once you actually train your system, you get your data set, you do the training, you have your ML model, and then you are using your machine learning model during the inference. If you think about this machine learning model, this is nothing but a piece of code, right? A piece of code similar to any other piece of code that you have, similar to your operating system, similar to any application that you're running in the system, and so on and so forth, right? So any attack that we kind of discussed in this course before, including that the adversary can do maybe buffer overflow, the attacker might do, changing the voltage in order to create faults, do return-oriented programming to attack the system, and all those things also do apply to this machine learning algorithm itself, because at the end of the day, this machine learning algorithm is nothing but a piece of code that runs on a piece of hardware, right? So basically, all we do in any other software or in any other system also directly applies to machine learning itself. So we might be able to do some false injection. We might be able to do maybe some side channels attacks, as we're going to discuss later in the course, and all those things. Okay, so it's not like machine learning is all of a sudden something special. At the end of the day, it's just one piece of code. So just keep in mind that all those other things that we discuss in this course do apply to machine learning systems. Okay. So this is kind of like, a nice summary of what's going on. So basically, you can attack during the data collection, you can attack during data processing, and during the training phase, basically, this is the majority of the poisoning attack. During the inference, what you will do is what's called the evasion attacks, as we said. And finally, during the integration phase, this is just a regular type of attacks that we can do in any other system that you use in your computer. Okay. So, and then these are basically some of the defense mechanisms. Some of them we already talked about. The others, if you're interested, you can go and read about them. But don't worry, you don't need to know exactly what's going on in all of these, but just have a general idea of the potential attacks and defenses at each different stage. Okay. So that's it with the machine learning security part of this lecture. Any final question about this before we move on to the next? Awesome. So if you remember, we said that the machine learning system could be a target. And we said that if the adversary wants to attack the systems, generally there are two things that the attacker is interested in. The first one is kind of like impacting the system in order to create some faults. And that would be basically fooling the system or changing the outcome of the system. And we said that this is basically a security issue. And so far, we discussed various ways of attacking the system and impacting the security of the system. Now we want to actually focus on the second possibility for the attacker, and that's attacking data. Okay, so that's attacking the IP or the information in the system. And this data could be either the inputs themselves, or could be the model or the weights of the model. Okay, so as Andrew was suggesting, right? So one thing that the attacker can do is, for example, reverse engineer your model in order to extract something. So we're going to now discuss how this can happen and why it's important for us to care about this. So first of all, why the attacker is actually even interested in extracting this information from this system? Why should we care? There are two things that we need to kind of keep in mind. Number one is that most of the scenarios for machine learning, there could be that some sensitive data is involved in your system, right? So for example, think about companies or industrial settings where you want to train a machine learning system based on some sensitive data to make some sort of inference. So a very intuitive example is a medical system. So these days, for example, clinics and hospitals and generally physicians, what they do is they, for example, take the X-ray of a specific part of your body, and then they apply image recognition and image detection to, for example, detect fractures, detect tumors, or detect various things in your system. Okay, and And in order to do that, they use, deep neural networks. They use very sophisticated machine learning algorithms. Okay. And in order to train the system, obviously, what they need to do, they need to collect lots and lots of these X-ray images with the labels. They need to train their system, and then hopefully they have a system that is very accurate. So next time that the new patient comes in, they take an X-ray, they feed it to the machine learning model, and they are able to actually detect that, for example, whether this person has this tumor or not, whether this person has this specific problem or not, right? And this is actually one of the key parts of the revolution of machine learning, actually, that these new classes of problems can be solved with machine learning pretty effectively. But in terms of the adversary and the attack and security of the thing, it's important to know that if the attacker, for example, the attacker can actually extract two things. One is if you have your model, basically, this X-ray model, the attacker can extract two things from your system. First, the attacker can extract the model itself. So, for example, if the attacker can extract this and creates this, so let's call this M. If the attacker can create this M prime, which M prime acts very, very similarly to M, then the attacker basically can steal the the IP or the proprietary information about this system. So think about now that the attacker or the adversary is hospital number 2 or hospital B, and hospital A or clinic A spend thousands and thousands of dollars to build this model because they need to collect lots of X-ray, they need to spend hundreds of time for designing this and so on and so forth. And they are now earning a lot of money by using this model in their clinic. So if the other clinic is losing business, what they can do is somehow figuring out what this model is and how this model works. And if they can replicate this model in their own system, then they can also provide the same service with almost zero cost, right? Yeah.
Is this done only by looking at the data inputs, outputs, or
Yeah, so we're gonna talk about how we can do it, but for now let's focus on why we want to do it. But yeah, that's basically what we're going to do. But imagine that just magically we can do it. It's just important to understand first why we want to do it and why it should be, right? So in this scenario, basically what the attacker does is stealing the proprietary information that in this case, the actual victim spent thousands and thousands of dollars and maybe hundreds and thousands of hours to create, okay? So it's kind of like competitive advantages for the adversary. So that's number one that the attacker can do. The other thing that the attacker can do is if the attacker can actually reconstruct the training data set that being used for training the system, the attacker can then access to the public, to this private information about the patients, right? So think about that the attacker can know what is these individual records, what is, what's the name of each of these individual patients, what is their data, and so on and so forth, right? So at the end of the day, what the attacker can do is understanding and kind of reverse engineering the system in order to extract this sensitive information about the inputs itself, okay? And again, there could be, then the attacker can use this for example, asking for ransom from people, for invading their privacy, and so on and so forth, right? So lots of different scenarios could happen once the attacker has this knowledge, has access to this large data set that potentially is sensitive. Okay, so this is why we need to care about the privacy aspects of things for machine learning. Is there any question here? Clear? And one thing to pay attention to is why all of a sudden machine learning, the privacy aspects of the machine learning is becoming more challenging. Because this is actually something that can happen for any system, but it's interesting to know why for machine learning this is particularly a big problem. And the answer to that is this this computation paradigm called machine learning as a service, right? So the machine learning as a service is actually a very interesting, new ability that these large companies provided to us. So this cloud system here is usually a large company that provides services. This is usually Amazon Web Services, Microsoft Azure, etc., etc. Okay. What they do is that instead of saying that, oh, you want to train a very complicated machine learning model, so you have two options, right? So you can either train it locally. So locally, you have to collect data, you have to find the model, you have to train it, and then you have to maintain it, right? And for every model that you want to use in your system, you need to do this. And now think about this: many thousand, small businesses, clinics, different companies, and so on. If they want to use any sort of, these deep neural networks for their own purposes, they need to do all these things by themselves. So machine learning as a service is basically telling you and giving you a different option. It says that, you know what, all you need to do is just collecting the data, send the data to us, and then we're going to do the training for you, we're going to do the modeling for you, we're going to do the maintenance for you. And basically all you need to do is through some APIs, you can query this model through the internet, and then we're going to give you the response. All right. So we're going to house this model, this service for you, and then you're going to just pay us. For example, pay per request. You can pay us, and this way you don't need to be worried about all the hassle of housing the system on your own computer and having your local system. Okay. And this is becoming more and more interesting and more popular these days. Almost most of the companies, specifically smaller companies, are using this in their systems. And as a result, we basically do see that this machine learning as a service is becoming a very, very booming and very profitable business for companies like AWS.
When you say modeling, does it mean like figuring out how many layers do we use and all this stuff, or what does it mean modeling?
So usually, I mean, these services even they give you the structure. So all you need to do is giving them the data sets, and they will figure out what model to use, what's the best model to use, and so on.
So, but usually, what does modeling refer to?
Yes, modeling basically means that what is the structure of your system, like how many layers you have, whether you're using CNN, whether you're using RNN, how deep your neural network is, and so on and so on. Okay, so machine learning as a service, great product, very, very helpful in many businesses, and kind of like this is one of the key factors of this very significant boom of machine learning in systems. But there are unfortunately problems that are coming up with this model. To understand that those problems, we need to actually look at this machine learning as a service and see what are the players and what are the potential attacks. Okay. So typically in machine learning as a service scenario, there are three players. All right. There is what's called the data owners, which we usually call it participants. So these are the owners of the data set itself. These are people, there could be one owner, it could be multiple owners, could be crowdsources. So these are basically just inputs that they collect over time with their labels. So for example, in the X-ray example, the data owners would be the actual patients, right? Then there is the server or the model provider, which basically is the actual, hardware that provides this service to us. This is where the training can happen. This is where the inference also can happen, all right? And finally, there is users who actually use this system once it's trained, okay? So the users are basically those that, interact with the system and tries to label their data, okay? So basically kind of like, this is the hospital, this is the data, This is the interface between the server and the user. And the server is basically where it houses all these machine learning models. And the users are the ones that query this model in order to get the classified data. Okay? So there are two types of attacks that can happen in this scenario. The number one attack is when the server becomes the adversary or the malicious. So in this case, what the attacker tries to do is finding this confidential data. It's extracting this confidential data, right? Because since the server is the attacker, the server already has access to the model, so the model is no longer secure. But what the attacker tries to extract is this data. So this data could be the data during the inference, or it could be the data during the train. Okay? So that's number one, the one possible attack. The second possible attack is when the user itself is malicious. And in this case, the attack is trying to basically finding this models and reverse engineer this model, right? So this is basically that hospital A, hospital B scenario that I described in previous slides, where somebody wants to try to reverse engineer the system in order to extract the models. Okay, any question from here? Okay, so just quickly recap, the privacy attacks in ML system tries to steal some data about the system. This data could be either the input data or could be the weights. The reason that we are seeing this privacy attacks because we are extensively using machine learning service as a main paradigm for our machine learning systems. And in this scenario, either the adversary could be the user, and the goal of the adversary in this case is trying to reverse engineer the model, or the adversary could be the model itself, the server, and in that case, the goal is trying to extract the input data. Okay, so now I'm gonna start discussing what are the possible attacks and how we actually launch these attacks. Specifically, we're gonna talk about 3 different types of attacks, and we're gonna show how we can actually achieve this. Before that, let's have a 5-minute break and then come back and talk this third. All right, so let's continue. Um, so we said that basically two different options, right? Either the server could be the adversary, tries to steal the data, or the user becomes the adversary and tries to reverse engineer the model. Okay, so let's actually go through these two one by one. So let's just start with the scenario where what if the user is the adversary? Basically, that's bottom one. Okay. So first question is what the user can steal. We already discussed this. Basically, the user can try to steal two main things. One is the model weights. So we kind of like reverse engineer the model. And when it does that, when the user does that, it basically gets the base, gets the structure, gets some features. Another thing that the user can do is basically tries to find this training data that used for this model. We're actually going to discuss why this is important and why this is why does it matter. Okay. So let's start with this first scenario where the user is the adversary, and what the user tries to do is reverse engineer the model. Okay. So we usually call this model stealing or model extraction attack. And the goal is that can a user who is interacting with this model, which usually in this case we typically assume a machine learning as a service model, can the user by just querying this model can reverse engineer and finally find the actual model. Okay. So basically the fundamental of this attack is that since the machine learning model is, as you said, it's a deterministic model, we can find some sort of equivalent function and functionality for this model, and all we need to do is basically guessing the parameters of this function. Of course, there are two questions we need to answer. First is what function should be used in order to model this attack, and then second is how do we extract these parameters. And the answer to both of those is that you can of course start with like maybe a linear systems of equation, or anything that sees that's works for you basically, but also kind of like balance between the accuracy and the complexity. But for example, for now, think about a system of equations of linear equations. And in order to find the parameters of this linear system, all you need to do is continuously and iteratively query the model and kind of build your system off of them. Okay? So the model extraction attacks is basically like this. So you have your trained model M, and this is the target model that you want to attack. As an adversary, you have list of inputs that you have created. What you will do is, let's put this inputs here. What you will do is you're gonna query this model and you're gonna get some responses. You're gonna feed these responses to your system of equation F. And basically this gonna give you some losses, right? And you're gonna compare the losses that you're getting here with the losses that you're getting here. And you try to kind of like, take these two actually. So you have your shadow model M prime, and the goal is to have M prime close to M. How do we measure the distance between those two? It's a separate question. But for now, just assume that we want to create a model that creates exact same outputs as the original model. Okay. So what we do is we start with some empty function. Let's say this is basically a function f, and in this case, f is maybe sigma of alpha ai's xi's. Okay. And all we need to basically figure out, this xi is the inputs, all we need to figure out is this ai's, and this basically coefficients for each of these inputs. And let's say this has the degree of n, okay? So basically this is n different coefficients. So we kind of need to figure out this coefficients. We obviously can start with some initialization value. So initially, AIs could be something random. And what we do is we send this input to the original model. We also send the same input to this shadow model. And we get the output of here and we get the output of here. Since we want to create this M prime to be very close to M, ideally what we want is that this Y prime and Y, the distance between these two is smaller than some threshold, right? So we want to create something that's create almost similar results always, right? So what you need to do is basically create this. You need to create this some sort of a loss here, and feed this back to your system, so that you basically try to change this coefficient 1 by 1, so that the next time that the same input goes into the system, the loss is less and less and less, right? And if you think about this, it's basically the same way that we are training the machine learning in the first place, right? Originally, if you think about how do we, train our M, we always had set of inputs and outputs. We start with this, we got the label, we backprop this, and we try to minimize the loss, remember? So this is exactly the same idea here. At this time, instead of using the labels, the ground truth labels that we have here, we are using this label that we have queried from the model, the original model. So basically what we try to do is that we are trying to train this model F to be very similar to this model M. And in this process, we use the same set of inputs, but we basically, in order to compute the loss and backprop the loss, instead of using the labels here, we are using the labels here, okay? And other things are basically very, very similar to the same way that we are training the original machine learning model. We use gradient descent, we do all those things that we do in a normal system. Does that make sense? So that's the idea of the model extraction. You will read some papers and see that there's lots of complexity and there's lots of things that you need to be aware of. In the interest of time, I'm not going to go through them. So I'm going to just defer it to the paper presentation next week. But a few things to just have an idea about is again we are having the same issue that we had before, and that is white box versus black box. So what does that mean? So since we are trying to replicate this M with this M prime, the question is that whether this M prime should use the exact same structure and architecture as M or not. Because at the end of the day, all we care about is that this M prime creates this Y prime that is very, very close to Y, right? This could be happening using the exact same structure, or it could be two separate functions that just happens to have the same result, right? So if you have the knowledge of M, if we have the knowledge of M, then what we can do and what is more intuitive to do is using the exact same architecture and structure for M prime, because at the end of the day, we want to replicate M, so it makes sense to actually use the same structure. And that's when you usually say that this is a white box model abstraction, because we exactly know the structure and architecture of it. But that's not a requirement, as you will see in the papers. You actually, if you don't know anything about the M, and the only thing that you know is the set of inputs and outputs, then you still can kind of guess and go with the black box model, basically, where all you try to do is making some guesses, and what you try to do is making sure that these two functions are close to each other. Okay? So model extraction with black box assumption is also possible, and it's actually much, much more stronger because it doesn't rely on this fact that we should know exactly what the M model should look like. We can basically assume anything and then try to basically replicate the model. The second thing that's the biggest challenge for model extraction is what's the query actually give us, and how many queries that we can have. Because remember, at the end of the day, you need to go through these samples and query the original model to get this Y's, right? So if this queries is limited, then the amount of data that you can use in order to train your M prime model is limited, right? So that significantly reduce and limits your ability to train this model. Another thing that happens is, as I said before, sometimes instead of just giving you the labels, these machine learning models also giving you the confidence values of other classes. And as you will see again in the papers and in the literature, you will see that this significantly improves the ability of the attacker, because the attacker this way has much more knowledge and information to play with, and this improves the attacker accuracy and the attacker ability to extract this function. Okay, so generally, what you need to think about and care about is what is the query model, how many queries that we can do and ask this model from, and also how much information each query gives us. Okay, so that's number two. And finally, number three is what is the complexity of this model that we are trying to replicate? If this model is actually a linear model itself, something like a logistic regression or linear regression, then our chances for finding the actual closed solution, very accurate solution for M, is pretty high, because we are basically trying to solve a linear system of equations. But if you're talking about something like a CNN, which actually has linear and nonlinear, components in their structure, then of course solving this problem requires solving a nonlinear equation problem, which necessarily does not have a closed solution, right? So you can only estimate your M prime model and hope that your M prime model is pretty close to the M model. But you may not be able to exactly replicate with 100% accuracy because you cannot solve this nonlinear function. Okay? So these are the three things that you need to care about when you're doing the model extraction. Any question here? Cool. So now let's go to the second possible attacks, and that's what's called membership inference. Remember, again, still the user is the adversary, And what the user tries to do is exfiltrating some information about the model or something about it. So the first thing the adversary can do is extracting the model and replicating the model. And we call that model extraction. The second thing that the adversary can do is extracting the data sets, the input data sets that used during the training. And we usually call it membership inference attacks, okay? So what the membership inference attacks basically does is telling you, it's creating this oracle that basically says that whether this record has been used during the training or not. So basically, we are trying to reverse engineer the system in order to figure out whether a specific record has been used during the training or not, whether this specific method is part or a member of this model or not. Okay, so for example, let's say multiple different peoples in this class have contributed to model machine learning system, and now we have the model and the model is used. What this membership inference attack does is that trying to create this oracle, let's call it O, that basically if you send these inputs, so let's say these red ones is actually used during the training, and these blue ones are not being used during the training. It's just records that has not been used during the training. What we want from this oracle is basically takes these records as inputs and give us an answer that yes or no, where yes means that this record is part of the training set, and no means that this record has not been used during the training. And for example, in this specific scenario, ideally what we want to see is that for any of these red ones, this oracle should say yes, and for any of these blue ones, the oracle should say no. Okay. And you might ask, okay, what is the use case of this and why should we care? There are lots of use cases for this type of attacks. Generally, for revealing that whether something has been used during the training or not, could reveal sensitive aspects and features of the input, including the privacy aspects of your data, the privacy aspects of your user, and so on and so forth. And that could be very, very dangerous in particular scenarios. Okay, if you're interested to, yeah.
Wait, you said this is the oracle?
Uh-huh.
Did the attacker build it? Or
Yes. So the attacker, the goal is building this as an adversary.
And we wanted to pass all of the red tests, the original ones, and we wanted to fail over test.
Exactly. Exactly.
Oh, so
basically, you want a machine that tells you for any input record that you send it to, say that whether this input record has been used during the training or not. Basically, is it a member of a group or not a member of a group?
but what if it's like it's correctly guessed what's the outcome? Then how can we know if it was part of the red input or not?
So your oracle doesn't give you answer of the out, doesn't give you the label. It just gives you a label that says yes or no. So you train your oracle in a way that has only two answers, yes or no. So you send input records, and it's just, let's say the output is 0 or 1. 0 means no, and 1 is yes. So you want to have something like this. We're going to discuss how we actually get this. But just to give you a high level
So it's
of,
not giving a label, it's just saying if it was in the red set or
Yes,
if
exactly.
it wasn't.
yes. The label still comes from your original model M. This oracle is some other model that the adversary trained using some method that we're going to describe. And all it does is basically just say yes or no.
But I mean, if we have the red list, then why do we need to create this oracle model if we can just like put all the like red data in a list and just check if it's in the list or
So
not?
no. So we don't have this, we don't know which one is red or not, right? What the adversary has is this. Some of these are red, some of these are blue. Oops. the adversary don't know which one is which. Think about a list of unclassified. So think about this, that I take the names in this class and I take 80% of them to train the model. And I don't use the rest, the 20 to 20%, okay? Then I publish the list of all the names to the class. And I ask you to tell me which 80% did I use for training. So this membership inference is basically answering that question. So you as a user have no idea which 80% I use. But if you manage to actually launch this attack, then you can exactly say, oh, you use this 80%. And now think about that, those 80% maybe have something in common that is sensitive. So maybe those who pass this class, I use them to train, and those 20% didn't pass the class. So basically by membership inference, now you can tell who passed the class.
And we're gonna learn how they build the work.
Yes, exactly. But we know why we need the oracle, what the oracle is. Okay? Any questions? Okay. So now that we know how to build this and why this is useful for the attacker, which I just described, let's actually go into the details of how to build this. So building this is actually quite interesting. And the way it works is basically, I mean, the fundamental reason that this works and we can actually build an oracle like this is if you look at this example here. So for now, let's focus on this part on the right. So this is basically the training phase of your system. So all it does is that it takes a data set like this. It uses the API, the training API to build the model. So we are talking about a machine learning as a service scenario. So we have a data set, we use the API to train it, and now we have the model. So now we're done with this right part. Now let's focus on this left side. So during the prediction or during the inference, we have two sets of possible inputs, right? So either there are some inputs that coming from this data set, and we want to do the inference for them, or there are some inputs that are not coming from this data set, right? So you have possibly two classes of data that can be used in the system, right? So they are either from this data set or not. If they're coming from this data set, the interesting thing that the original creator of this attack saw was that the classification and the output of the system, basically this and this, where this darker one is from the inputs that are coming from this data set, and the lighter one is the inputs that are not coming from this data set. If you look at the confidence value of our classification, we will see that there is a difference between these two. And usually the difference is very significant when you are drawing an input sample from this data set or when you're drawing it from somewhere outside. And what this machine learning membership inference attack does is try to see that by seeing this classification value, it has to tell you whether this is an input that is coming from the data set or whether this input is not coming from the data set. And in practice, people have shown that there's just fundamentally, there's a difference between the confidence values from an input that is coming from the data set and the inputs that are not coming from the data set. And they're basically trying to learn those differences and build their oracle based. Okay? So again, to just repeat what I just said, what the attacker in this oracle tries to do is looking at the output of the inference phase and try to predict that whether this output is from an input record that was part of the original data set or not. And fundamentally, they found that there is a huge difference. There's a noticeable difference between those inputs from that data set and the other inputs. And so there is a potential for learning these differences and then basically creating this oracle with accuracy. Okay? So let me actually go a little bit into more details and tell you exactly how this works. So basically, this is how the pipeline for membership inference works. So you have a record, X, you use the API to actually query the model. The model is going to give you confidence value of all the classes that it has. Let's say this model has C different classes, and let's say, for example, C is equal to 10. So when you send this X to this machine learning as a service model, this is your original model. It's going to give you 10 values, usually between 0 and 1. So maybe 0.1, 0.2, maybe 0.05, etc., etc. And then probably out of which one of them is the value is really high, which is the output class. And what you want to do is you want to use this as the input feature to this oracle here. This is basically what the attacker tries to train. And the output of this, as I said before, is basically a yes or no answer. So if this X, this original answer for this is yes, you hope that this actually says yes. If the answer for this is no, then you're hoping that your oracle is actually saying no. Okay?
What is X here?
X is an input data. So you either get it in from your data set, or you're getting it from another data set that is out. So again, back into the example that I gave you. X is the names of the people in this class. From the list that I used to train the model, if X is part of that, you hope that your oracle say yes. And if it's coming from the rest of the class that I didn't use for training, your oracle should probably say yes.
But how would it know? I'm so confused, like how would it figure out what's the original training set?
Oh, so this is actually the next slide I'm going to tell you about how we do that. But you're getting there. All right. So exactly for knowing how do we do that. So how do we train? So now the problem is training this, right? So in order to train this, we need labeled data. Okay, because for training any machine learning system, any classifier, you need labeled data. So how do we create this labeled data? So basically, first of all, the inputs to this oracle are confidence values. And then, as I said, for example, just imagine for now to make things simpler, think that there are 10 different values that gets to this oracle. And your output is basically just a simple yes or no. So it's 0 or 1. Okay? So here's how we're going to train this model and how we're going to test this model. So it's actually quite clever. So what we're going to do is that we're going to get our, let's say that we have access to the input training set. What we're going to do is we're going to divide this into 2 pieces. Let's say divide it in half or whatever distribution that we want. Then what we're going to do is that we're going to train our what is called a shadow model or SM. And we're going to use this data set to train our shadow model, right? And we can use the same API to train this shadow model. For now, just don't worry about this part. So we have our shadow model trained. Now what we're going to do is we're going to send this input data set that we use during the training, and the second half of the data set that we didn't use for training. And we're going to train this, we're gonna query both of these and gets the classification values for this class of input data sets and this class of input data sets. So we're going to get this list and we're going to get this list. But the key here is that since we exactly know which one we use for training, which one we didn't use for training, we know the answer of this yes or no for this specific records here. So anything that's coming from this part, the answer to it should be yes. Anything that's coming from this part, the answer to it should be no. Okay? Give me a second. So now what I'm going to do is that I want to train this model, right? So I'm going to feed both of these records, all the records from here and all the records from here. And now I actually have the correct label, the ground truth label for both of these as well. And now I'm going to actually train this model using all these records that I have here and all the records that I have here. And after this process, now I will have the Oracle model that's been correctly trained.
This means that the adversary must have the entire data set.
Yeah, so great question. And the answer to that is that this data set has nothing to do with the original data set, right? So what you do is that you get the data set, and actually we will briefly discuss this, that how to pick this data set. But this data set is what the adversary picked, whatever they want, okay? Let's say they look at the previous years as class names or another classes and get those names. All the main trick that the adversary used is divide that data set that it has into two pieces. It's going to use one piece to train a model. And this is a shadow model. This is not the original model because, of course, we don't have access to the original model. But we create a model that is very similar to original model. And how do we create that? Basically, we either query the same model or we use something like a model extraction to actually build that replica. But for now, assume that we have a replica of the original model. Then we're going to train that replica one time with the data set number one. Not one time, it's just with data set number one. And now we have this model, and now we are going to query this model with these two groups of data sets, groups and records that are coming from group number one, and the records that are coming from group number two. But the key here is that since we trained that model with this group number one, we know that the answer to anything that's coming from group number one should be yes. And the answer that anything that's coming from group number two should be no, right? So we're going to use that to train this oracle, basically. And if we have this data set large enough, then we can train a very accurate oracle model.
So data sets 1 and 2 are not related to the original data set?
Not related to the original data set, yes.
And
But usually they're coming from the same distribution. So they're coming from the same data sets. The adversary basically just divided it into two pieces.
And one of them will output yes, and one of them will output no.
Yes. Why? Because we trained this model with this data set number one. So of course, anything that is collected from data set number one should be yes, and anything from data set number two should be.
So would it be for both of them f1 of x, or would they be like different?
So labels could be different. So labels could be anything between 1 to C. The labels doesn't matter. The distribution and the difference between the labels is actually what the model will learn.
Okay, and one last question. Why don't we just use then the shadow model, since isn't it like in a way the same thing as the oracle?
No, the shadow model gives you confidence values. It doesn't tell you whether so remember, we are doing two things, right? So you're kind of mixing up two things. So you have a model, you have an input, and you want to classify this, right?
Yeah.
So that is your original model, and that is kind of what your shadow model also tries to do, okay? They just classify, you just say that, for example, let's say your inputs are different images, it just tells you what that image is. Is it a chair, is it a desk, is it a camera, whatever, right? What we are trying to do here is that out of all those inputs, how many of them has been used during the training, and how many of them has been not used to train? We are trying to answer this question, and this question is not relevant to what this image or what this record is. That's a separate problem. Okay.
Yeah, but doesn't the shadow output shadow output just yes or no here? It doesn't output the classification.
It just outputs the classification. It just tells you whether this is a chair or whether this is a desk. But how do you know that whether this desk has been used during the training or not? That's where the oracle comes in.
Oh.
Right? So basically, as you can see, the input of the oracle is the output of your model. Okay? And on top of, so your output of the model is just this confidence values, this F1 to FCX. And this no and yes is what we added as the label. So basically, we know that this vector of 10 numbers, we know the answer to that. Some of them are yes, some of them are no. We have a data set of this. We feed it to this Oracle model, we train it as we normally would. And now we have the trained model that can very accurately tell us whether the specific vector is part of the input data set or not. Does that make sense? So this is basically kind of like, how do we create the, this is kind of like, how do we do it in a normal attack scenario? So typically, as I said, you create some shadow models based off the original model. You use that with another training data set to build your attack data set, this thing right here. And now during the actual attack, you get these records one by one, and basically this attack model here will tell you whether this record was part of the training or was not part of the training. And this way you can basically classify and label these things one way. Very cool. Oops. So one final thing before we wrap it up, the third type of attacks is what's called a model inversion or reconstruction. Okay. So instead of for membership inference, what we are trying to achieve and what we are trying to reconstruct is the membership of the inputs, right? So to tell what if I see this record X and this record Y, can I say was this part of the input data set or no? And the same for Y, yes or no. Okay. But you might wonder that can we actually extract more things about this input records? And maybe if I have some partial inputs such as X and Y, can I build a model that if I feed X and Y, maybe it also gives me information about Z, about T, about others, which also records that being used during the training. Okay, so maybe let's say that back into the names problem, when I use 80% of the class names to train a model, I publish 50% of that. And maybe if you use that 50% and develop these new attacks, you can also reconstruct the remaining 30%. Okay, so basically you are extracting and reconstructing more information about the inputs, and this way you can actually kind of like even revealing more sensitive things about your inputs. Okay, this is typically what's called model inversion or model reconstruction attacks, where the goal is trying to reconstruct something about the input data that you don't have. Okay, so for example, one example that I'm showing here is that let's say you have some auxiliary knowledge about your inputs. So for example, your inputs are blurred, your inputs are masked, and you have a collection of these, but you don't necessarily have you don't have this original records. Okay, so what this model inversion attacks tries to do is that if I have a collection of these auxiliary knowledge, what I want to create is this original inputs. And this, of course, reveals, for example, in this specific case, reveals people identity, right? All these things try to do is blurring this image so you cannot tell who this person is, right? Or you're trying to mask it, you're trying to do different things to retain the privacy. And what this attack does is that it says that if I have enough knowledge about this, if I have enough records of this blurred image and this mask image and so on, maybe I can reconstruct this image and basically negate or nullify the impact of those privacies. Okay, So this is basically what the model inversion does. I'm not going to go through the details of how exactly it works, but you need to understand another class of machine learning systems called generative adversarial networks, or GANs. What this generative adversarial network does is that basically it learns from these kind of auxiliary information how to reconstruct a bigger image, basically. Okay, how to reconstruct another class of input. So it's a generative network. It's not a discriminative network. It's not trying to classify the problem specifically. It tries to reconstruct the image based on some inputs. If you're more interested about GANs, I definitely recommend you to go and read more about them. But generally, the idea is that it tries to learn the features and try to reconstruct some of the features that it hasn't seen before. And this way, you can finally reconstruct this image and create a new data set. Okay. So of course, the success rate and the complexity of this attack depends on what auxiliary information is available and how much it is. It's not like for any auxiliary information that you have, you can easily and correctly and accurately create the system. But actually, it's surprisingly and alarmingly successful, these types of attacks, unfortunately. So people have shown that if you have a collection of blurred images, you can actually create an actual, well-constructed and pretty accurate image. Okay, so this is basically the idea of model inversion, similar to the previous ones. Knowing the original model and whether you have white box or black box access to the model have a significant impact to the system. But to just summarize what we are trying to reconstruct is we are using these generative models that we get some partially available information. And what we're trying to do is either creating the entire record or either trying to build some other features that at that point we don't have access to. Okay? And this is basically what we call the model inversion attacks. It's much more sophisticated and much more difficult attack to do, but people have shown that this is also possible for some class of attacks. Okay. Any questions? So to wrap up this part, let's also talk a little bit about defenses. So there are a range of different solutions because we talked about multiple different attacks, right? The main ingredient in all these defenses is usually adding noise to the response. So remember that when we, for example, talk about model extraction, we said that we are basically querying the model, and then we are trying to basically reduce the loss between what we are querying from the model and what we're getting from our own shadow model, right? So one way of protecting our system against being reverse engineered is that instead of sending the actual output, we're adding some random noise to our output as well. And this way we kind of like make our behavior a little bit more non-deterministic, right? So we add some probabilistic behavior to our system, and this, as people have shown, this makes this reverse engineering task significantly more difficult, because not only the attacker needs to figure out what is the best mapping between y and y prime, but it also needs to deal with this R, and it has no idea what this R is because this R has been created randomly. And this way, the attacker has much more difficult, more difficult job to predict this ball. But also, it's important to mention that adding noise to your output label also impacts your overall accuracy. So it's not like, yes, that makes sense, we just add a lot of noise to our output, and this way we are secure. If you're adding output to adding noise to your output, remember that this is also where this model is going to be used, right? So for example, you want to use this to to classify whether this is a chair or whether this is a desk. And by adding noise to your output, you're basically saying that there is a chance that this is indeed a desk, and my model also actually classified this as a desk. But since I'm adding this small noise, now it might be classified as a chair, right? So you're basically, by adding this noise, you are reducing your accuracy of the original task as well. And the interesting thing is, as you add more and more noise, the chances that the attacker can actually detect what this model is reduces. So in order to achieve more privacy and more security, you want to have bigger noise. So bigger noise means better privacy. But on the other hand, bigger noise also means lower accuracy. Okay? So if you look at the privacy accuracy trade-off, you will see that you want to have larger noise because it means that the reverse engineering tasks become more and more difficult. But on the other hand, your accuracy drops. And that's not what you want, because at the end of the day, you want to train this model to be very accurate. And you won't be able to tolerate any loss in accuracy. So it is very actually important and very interesting trade-off between privacy versus the accuracy. And what you want to do is kind of finding the right balance between those two. You don't want your system to be not private at all, but also you don't want your system to be not accurate at all. So you want to find the sweet spot between the two. Similar to evasion and poisoning, protecting your model and your data set is again another solution. Because again, at the end of the day, the attacker needs to query your model multiple times. So if you use some methods to detect that potentially anomalous activity, you should be able to detect the potential adversary. Training your system and retraining your system using adversarial sample also helps. And monitoring the queries, trying to find the anomalies is also another possibility for detecting the system, for protecting the system. Okay. And there are many others that I didn't discuss. I think one of the papers actually discussed this, but generally the idea here is again that you want to make the life of the attacker much more difficult, either using some detection mechanism, either by increasing the attack, decreasing the attack surface, or by adding some random behavior to your responses so that the attacker cannot tell the difference between the actual input and some randomly generated input. Okay? Any questions here? All right, so one final thing to say before let you go is, so we talked about the scenario in which the user was the adversary and the server was the victim, right? But as you remember, we said that there could be the other way around as well, where the user is the victim and the server is the adversary. So what is that scenario? It's the scenario in which that the user wants to use this cloud service, this machine learning as a service scenario, but necessarily doesn't trust that server to just give them the data. Okay? So the answer to this problem is a class of solutions called privacy-preserving computation. Okay? So privacy-preserving computation, it basically says this, that if I have input X and if I have a function in cloud, how can I compute f of X without revealing what X is? Okay? So of course, one simple thing to do is that I'm going to send X to the cloud, and cloud going to compute the f of X, let's say Y, and send back Y to me, and everybody is happy. But I don't want to reveal exactly what X is, but I still want to compute what Y is, okay? And the privacy preserving surprisingly, fixed this and solved this issue. You might think that this is not possible, it's actually indeed possible. We won't go through the details of that, but just give you an example. one possible way of doing this is through what's called homomorphic encryption. So homomorphic encryption is actually doing this by adding encryption to the input. So if you remember about like RSA and AES, what we said was we're gonna have X, we're gonna encrypt X and create C. We will send C to the cloud, and the cloud we're gonna decrypt C and get X again, then apply f of X. It's gonna, again, encrypt it, gonna give us C prime, send back C prime. We're gonna decrypt C prime, and we're gonna get f of X, right? So this is kind of like the pipeline of sending and receiving things over encryption. But if you want to apply f of X, you cannot apply f of X on C and then decrypt this and get f of X. AES and RSA doesn't work like that. So in other words, you cannot do computation over encryption. If you want to do computation, you have to decrypt first, do the computation, re-encrypt, send the data back. Okay? So what this homomorphic encryption is actually exactly that what we want. So basically what the homomorphic encryption does is that, let's say you have an X and you want to compute f of X. What homomorphic encryption does is that it says that, oh, encrypt this and do C, apply f of X to this, apply f to this. So basically we're gonna get f of C, and this part is on the cloud. And then it's gonna send back this f of C, and if we decrypt this f of C, we're gonna get f of X. Basically, in other words, we are adding two encrypted values. We decrypted it's as if we are added them together. So for example, let's say I have number 2 and number 3. I'm gonna encrypt this and I'm gonna get C1. I'm gonna encrypt this, I'm gonna C2 using homomorphic encryption, not the regular encryption. Then on the cloud side, I'm going to add C1 and C2. I'm going to get C3. I'm going to send back C3, and I'm going to decrypt it using homomorphic encryption. And the value that I'm getting is going to be 5. And that's the beauty and magic of the homomorphic encryption. It's designed such that it can actually do this activity without any problem.
Could another way be to like just train the model on the encrypted data itself? Like, is that possible?
What would happen if you train a model on the encrypted data?
Yeah, like could the user just like encrypt the data and then give that as its data set and just train the server model on that?
But then the next, so it's not just the machine learning. You want to, for example, do additional multiplication. So privacy preserving is not necessarily about machine learning in general. You want to basically use it for any function. But what you're saying is right. So basically, that's no longer encryption. So the one that I didn't describe is basically encoding. So what you're suggesting is instead of sending the raw inputs to the cloud, how about I encode it first and I send that to the cloud, and then I build the model based on the encoded data. That's also actually another interesting way of fixing this problem, but it's not, the security you get from this is not guaranteed because first of all, it's not guaranteed that the attacker cannot reverse engineer and gets from the encoded cannot get X. And the second thing is the attacker may still actually extract some information about the system, but that's very interesting observation. Here, what we are suggesting is that it is guaranteed that the attacker can know nothing about the system because homomorphic encryption is as secure as RSA and as secure as AES. Okay, so basically, by seeing C1 and C2, the attacker has no idea what the original plain text was. Okay, so back to the homomorphic encryption scenario, what we are basically saying that is homomorphic encryption is this specialized encryption mechanism that what it does is allow us to do computation over encryption. And the state-of-the-art homomorphic encryption supports both multiplication and addition, so both of these. And probably you know that if you have the capability of doing addition and multiplication, we basically can compute any polynomial function that we want. You still cannot do nonlinear activity, but at least linear activities you can easily. Okay? So, a state-of-the-art homomorphic encryption gives us the ability to do this. And this way we can kind of like, we never send the raw data to the cloud. We always encrypt it using homomorphic encryption and then send it to the cloud. The cloud treat this as a normal input, so you just do the addition and multiplication over that, send us back the results. We decrypt it, we get the results that we want. And then in the whole process, cloud has no idea what's happening. Okay? So that's it for today, where basically we talked about privacy and security aspects of machine learning. We talked about different attacks and defenses. And this again was one example of a complex system and how an attacker can impact this at various levels. All right, thank you guys.
Next meeting, only up to materials cover.
Yes.
Thank you.
Yep.
Thank you, Professor.
Yep.
When was the last?
Yep.
Whether it doesn't project properly.
1 second.